We have now explained that we can use a resistor as a sensor. For example, we can use a resistor to measure strain, or to measure a temperature, or to measure a magnetic field. So let's now look in what would be an efficient way of actually getting a signal out of a resistor. Consider a resistive sensor such as a strain gauge, and consider this resistive sensor to have a fixed value R0 plus a value delta, and the delta will be the varying part that depends on the physical property that I want to measure, for example, the strain. Now, an easy way of measuring a resistance is to send a current through it and actually measure the voltage change over it. So let's send a current through this resistor. We can do that by adding another resistor on top, which we can choose to also have a fixed value R0, and then put a voltage E on top and couple the bottom to ground. And now I will see that between these points, 2 points here, I will be able to measure a signal U that equals U0, which is plus U delta. And U0 is the voltage, is the voltage determined by the fixed value R0, and U delta will be the varying part dependent on my physical property that I'm trying to measure. And I know that U0, because I have two equal resistances R0 here, I know that U0 will be equal to E over 2. Let's make a graph now to see how this would typically look like. So you make a graph of voltage V versus time, T. And I can draw my value E here. And I can draw my value U0 equals E over 2 here. And I can also draw, this is of course a constant, U0. I can also draw U delta, the real value U, which for example looks something like this. This is U, and this part here, for example, this is of course U delta. Yeah, so U equals U0 plus U delta. Now the interesting part in my signal here is really the U delta. The U0 doesn't tell me anything. So I want to extract the U delta part. How can I do that? And also interesting to know, of course, the U delta will be much smaller than typically than the U0. The U0 will typically be signal in the order of a couple of volts, and the U delta may be signal in the order of millivolts down to microvolts. So this U delta is really much smaller than the U0. So how can I now subtract the U0 from this value? So one way of doing that is to keep on considering the same setup, but next to it, build an identical copy, but now consisting of two resistors R0, such that at this point I know I will have a value E over 2. And at this point I have the value U. So now I know that if I want to know U minus E over 2, I just have to measure the difference between these 2 points here. I will call that S. S equals U minus E over 2 equals U delta. So, and where does that point lay on the curve? Well, I simply subtract E over 2, and I see that my signal S will lay exactly here, and it will look something like this. I can now simplify my scheme a little bit by, of course, coupling the ground together. Ground is ground, so, and we have only one voltage source here, fixed voltage E. So I have now what I call a Wheatstone bridge, consisting of two current arms, each with two resistors R0, and in between I can pick up my signal U delta. And what I can now do is take this signal U delta, for example, and send that to an amplifier. For example, I can amplify this 100 times in an amplifier, and then I'll get something that an amplified signal would then look something, for example, like this. It is of course very interesting that I can go from this signal to an amplified signal, because I wouldn't be able to do that with the blue signal U here. If I would amplify this signal with a bias that is E over 2, I would also amplify the bias, and my signal level would become way too high to be able to handle with electronics.